All right, we are going to graph this exponential function right here, y equals half times 5 to the x power. Now, there's little tricks that you could use to graph exponential functions, but what I'm going to do is I'm going to make myself what's supposed to be a t-chart. Looks terrible. But what I'm going to do is I'm going to substitute in 0 for x, 1 for x, figure out a pattern before I even bother with these guys right here. Now I'm going to plug in 0 for x. I'm going to do that a little bit mentally, but also write a little bit off to the right. So if I plug in 0 for x, that's going to be 1/2 times 5 to the 0th. Anything to the 0th power is 1. So that gets me half of 1, which is a half. So plugging in 0 gets me a half. Now, a trick that we can learn here is whenever you plug in 0, whatever number is being multiplied to our power, that's going to be your y-intercept. Fun fact. All right. As long as you're not adding anything over here. Don't want to screw that up. Now, let's plug in 1 and see what happens. Okay? If I were to plug in 1 for x, 1/2 is still lingering. 5 to the first power is just 5. Okay? That ends up with 5 over 2, which is 2.5. Now, the pattern that we're figuring out, right, is as x goes up by 1, my fraction, or whatever number this is going to be multiplied by 5. So the next guy is going to be 25 over 2, because as x increases, y gets larger by multiplying it by 5. 5 over 2 times 5 is 25 over 2. In reverse, as I lose an x value of 1, this guy divides by 5. So if I were to take 1/2 and divide it by 5, that's the same thing as multiplying it by a fifth. That gives me a tenth. So that allows me to draw a few points. So -1 is basically 0. I mean, 1/10 is close enough to 0. 0 1/2. 1 2/5 is 2.5. 25 over 2 is 12.5. And if I were to multiply by 5, I'd definitely run out of space. Okay? But what we see is as this guy goes to the right, it gets super big, super fast. As it goes to the left, it gets super small. And this is just going to keep getting smaller and smaller and smaller and get awfully close to 0, but never technically hitting 0. So this is an example of exponential growth. If I knew how to draw pictures correctly, this is going to look absolutely terrible. I'm going to start that over, pretend that didn't happen. Look at it. Look at it. Looks like a hair. Scooch it over there. Let's try one more time. Still staring at me. Let's make it nice, and yeah, maybe if I kind of do like a sketch way of doing this, nice and flat, gets bigger, gets bigger, gets bigger, gets much bigger, much bigger, much bigger, much bigger. And even though that still looks god-awful, that's what it is. Exponential growth. Don't judge me on my artistic talent. Judge me on my brain, which is slightly above average. But there you have it. We need to solve this exponential equation right here. Now, eventually you're going to learn something called logarithmic functions that would do the job for you, but that's not what we're going to do here. There's a little rule that says if you have, let's use 6, just for fun, 6 to the a equals 6 to the b. Well, since these 6's are the same, then we can legally say that a equals b. These exponents are the same. Let's just leave that over there. Let's just leave that over there. Why am I saying that? Well, if I can make 36 6 to the something power, like, I don't know, 6 squared, then I'm in great shape. 36 is 6 squared. This stays 6 to the negative 3v minus 2. And since these 6's are the same, then these two are the same, and I can set them equal to each other. So negative 3v minus 2 equals positive 2. And now it's just an algebra 1 problem. Add 2, cross u out. negative 3v equals 4. Divide both sides by negative 3, like that. And 4 over negative 3 is the same as negative 4 over 3. So if you can make the bases the same, you're in great shape. If you can't, you're going to learn something called logs. That'll do the job for you. This is going to be terrible, but this is solving an equation where you have variables in your exponents. So what we can do is we could try to turn this into just one thing looking equal to one thing. So what I'll do is I will rewrite this guy as 16 over 16 to the negative 1 to the x. Now, what did I do? If you have 1 over 16, if 16 is in the denominator, move it to the top part and make it to the negative 1. That's going to equal 1/4, which, I tell you what, while I'm at it, I might be doing a bit too much here, but while I'm at it, I'm going to turn 1/4 into 4 to the negative 1. For the same exact reasons that I did that over here. That's all the 2 to the 2 minus 2x. Too many 2's in this problem. Now, if I wanted to, if I have a power to a power, you multiply the exponents. So this becomes 16 over 16 negative 1 times x to the negative x. Okay, equals, same rules apply here. Okay, if I multiply negative 1 to this whole thing, I use distributive property. So this becomes 4 to the negative 2 plus 2x. Now, I'm going to put an imaginary 1 here. Why? If I have 16 to the stuff over 16 to the stuff, when it's division, you subtract the exponents. So invisible 1 minus negative x can make this rewrite as 16 to the 1 plus x. That is still going to be equal to, nothing changes here, not yet, 4 to the negative 2 plus 2x. Now, in a previous problem, I had a very similar situation going on here where if I can take that 16 and make it 4 to this stuff, I'm in great shape. So I'm going to do that. 16 is 4 squared. I still have 1 plus x over there, and this is still 4 to the negative 2 plus 2x. Just like I did over here, I'm going to distribute that 2 through multiplication to 1 plus x. So I now have 4 to the 2 plus 2x equals 4 to the negative 2 plus 2x. Now that I have the same base, if these are the same, then I can say that these are the same. Now at this point, you should be saying, uh-oh. I have a 2x on the left. I have a 2x on the right. They go away. That leaves me with 2 equals negative 2. Does 2 equal negative 2? No. So what's my answer? There is no answer. All of that to find out that there's no solution. Ah, what a rip. But I had a great time doing it. Rewrite in exponential form. We have a log. Generally speaking, if I give you something in this form, log base b, and let me get all colorful, log base b of a equals x, so many colors. If I give you something that looks like this, I'm allowed to rewrite this as b, so the base is still the base, x for exponent, b to the x equals a. So what I need to do here is I need to take a look at this guy and compare this to that guy and say, all right, well, b is my 7, 49 is my a, and 2 is my x, which I made purple. going to stop with the colors because it's taking me way too long. I can write that as b to the x, so 7 squared equals a, which I called 49. So fun fact, this is a true statement, making that a true statement. But this is how I rewrite something that's in logarithmic form into exponential form. No solving, no completing anything, nothing to simplify. That's just me changing log into exponential. That's it. All right, my job is to evaluate log base 4 of 1 over 64. Now, if you look at a calculator, you're not going to find log base 4. However, what we know how to do is we know that I can rewrite a log into exponential form. So if I give you something in the form log base b of a equals x, I can rewrite that as b to the x equals a. Now, if you look at this, you might be thinking, well, that is not the same as that because it's not equal to x. So let's make it equal to x. Why not? I'll label you b. 1 over 64 is my a. So I can rewrite this as b, which is 4, 4 to the x equals 1 over 64. Now, right now, there's not much I can do, but I do know this. I do know that if I can make these guys the same exact base, life is a lot easier. So if I write this as 1 over 4 to the third, because 4 times 4 times 4 is 64, and if I take that 4 to the third that's in a denominator, move it up into the numerator, and make the exponent negative, I now have two things that have the same exact base. If 4 equals 4, if the bases are the same, then these exponents are the same, and I know that x equals negative 3. So, what is log base 4 of 1 over 64? Negative 3. I probably shouldn't have circled this guy because there was no x in the original problem, but the answer is negative 3. So there you go. Find the inverse function of y equals log base 5 of negative 2x. All right, whenever you're trying to find the inverse, the first thing that you do is take the x and the y and swap it. So I'm going to make this x equals log base 5 of negative 2y. What I need to do is I need to solve for my new y, but this is an absolute mess. I mean, y lives inside of a log inside of a parentheses. This is terrible. So let's turn this into exponential form. Okay, so exponential form, I have 2 videos where I do this. So this will become 5 to the x equals negative 2y. And my job is to now solve for my new y. So I divide both sides by negative 2, both sides by negative 2. Cleaning that up will make this look like, let me move this y over here, y equals 5 to the x over, let's put that negative out there, over 2. And now that y is all by itself, I can throw the inverse symbol to it, and I have my inverse function, y to the negative 1 equals negative 5 to the x over 2. You might be able to write this out. Some teachers might want you to write this out as this so it looks more like exponential growth or something like that. Some teachers might want you to say, all right, well, bring that 2 out, make it negative a half times 5 to the x. Either way is fine. They're exactly the same. They're exactly the same. It all depends on your teacher. Condense into a single logarithm. All right, well, I have 2 logs being connected by addition. The first thing that you always want to do is if you have a number living in front of a log, like this one right here, there is a rule that you can take that number and make it the exponent inside the log. So I can rewrite this as log of y to the fifth. I like to put parentheses around there. It just looks better. Okay, log of x, nothing happened there. Nothing at all. When you add two logs, you multiply the insides. So log of x plus log of y to the fifth is going to be log of x times y to the fifth. And there you have it. If I were to subtract these logs, you would divide, but in this case, I added these logs. So x times y to the fifth is x y to the fifth. X has its own person. Y has that 5 attached. It is now a single logarithm. Fun, 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 fun. Condense into a single logarithm. All right. First thing that you want to do is if you notice any numbers living in front of a log, which I have here, and I also have here, you're going to want to take those and make those exponents for the things living inside the log. So I'm going to make this first guy log of, and I like to put parentheses, it just looks better, log of u to the 6 minus log of v to the 6. If I were to add these, I'd multiply. However, since I'm subtracting logs, you divide, and you always go in the order that you're given. So since this is a negative, this becomes my denominator, and since this log is positive, it's my numerator. And so by putting these together, I have log base 10, invisible base 10, of u to the 6 over v to the 6, and I am done. Okay, nothing more to do. Now, some teachers might be like, well, I noticed that there's a 6 in common with each of these, so if I wanted to, I can write this out as log of u over v, and since both of them have a 6, I can throw a 6 right there. You're allowed to do that. To me, it's not necessary, but don't be surprised if you have a teacher that asks you to do that. It's perfectly possible, perfectly fine. But yeah, either one of these work just fine for me. My job here is to expand this log into multiple logarithms if that's what I'm going to get. And so the first thing that I'm going to do is I'm going to rewrite the cube root of x as an exponent of not cube root. So the cube root can be written like this. And I always like putting things in parentheses, especially logs in parentheses, x to the 1/3 power. If I have a log and I'm supposed to expand it, make it look larger, what I can do is if you have an exponent living inside your log, bring it out front. So this now becomes 1/3 log of x. And believe it or not, that's it. There's not much more I can do with this unless I want to rewrite it all over 3, but that's kind of pointless. I mean, expand means take everything on the inside and rip it out so there's nothing but x's and nothing else. So that's what I did. That's all I have to do. I'm done. All right, my job is to expand log parentheses u times v close parentheses to the 6. So I might have several logs going on. First thing that I notice is I have an exponent living right here. My exponent is attached to the whole thing, okay, and not just u and not just v. So the first thing that I want to do is if I'm supposed to expand a log and I see an exponent that applies to everything, bring it out front. So now I have 6 log u times v. Now I'm going to throw this in brackets just to demonstrate what happens next. If I'm multiplying stuff inside a log, what I do is I split it up through addition. So 6 is still living out here. Log u times v becomes log u plus log v. That 6 that's living out there gets applied to both of these. So this is now 6 log u plus 6 log v. And this is further stressing the point, stressing the fact that that 6 applied to both u and v and not just one, and that's why the 6 lives in front of the u and lives in front of the v. All right? So now that I have just a u and just a v, everything's ripped apart. That's me expanding this guy right here. Dunzo. All right, my job is to solve 10 to the b equals 74. Now, back in the day, if this number was something like 100 or 1,000, we could just make this 10 to the number dunzo. But we can't do that here. If it's 10 to the b equals some number that you can't make this equal 10, we have to use logarithms. So what we're going to do is we are going to rewrite this as log. My base up here is my base down here. Whatever it equals goes inside the log, and my exponent up here is what it equals down here. Now, any log that you see in a calculator, if you go to a calculator and you see the log button, that automatically means log base 10. So what you do is you go to a calculator, you type out log of 75, and you'll find out that you get 1.869. Is there more? 2, 3, blah, 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 blah. Now, why such an ugly number? Well, first off, 10 to the first power is 10. 10 to the second power is 100. So my number is going to be something close to 2, but not quite 2. And it's going to be a terrible mess because I don't know what 10 to the what power is 74. So it's going to be something kind of close to 2. And in this case, it's that guy right there. All right, so that's how you use logs to solve an exponential function. All right, looks like we have to solve ourselves this terrible looking exponential equation. First thing we should do is just get rid of that 4. That's just lingering on the left. So subtract 4 from both sides. That gets us 17 to the k minus 10 equals 62. Now, normally when we see 17 to the stuff equals a number, we want to try to make this number 17 also to the stuff, but 62 ain't happening here with 17. So we're going to have to turn this into a logarithmic function and take it from there. So in order to turn this into a log, we make this log. Our base is also our base here. Whatever it equals is going to be inside the log, and that's going to equal k minus 10. Now here's the tough part. Whenever it just says log, that's log base 10. We throw it into our calculator, call it a day. But that's not going to happen here. This requires the change of base formula. Now the change of base formula says if you have something log base b of a, you can turn that into log base 10 or log base whatever you want of a over log base, same thing, of b, right? So log base 10 of a, you could also use ln of a over ln of b, but, you know, that's what I have here. So I'm going to write this out as log of 62 over log of 17 equals k minus 10. Now I'm going to write this over here where I have a little bit more space, split that into 2 parts. Let's find out what log 62 is. I have no idea. All right, log 62 is 1.79239, so I'll make that 4. Log base 17, according to the internet, is 1.23044, and that's still going to equal k minus 10. Now what I have to do is I have to divide 1.7924. I'm going to divide that by, and I'm actually literally doing this on a computer right now, 1.2304. That ends up being 1.4567. So let me write that out, 1.45675. So I'll actually make that 68 equals k minus 10. Now that I have something a little bit more manageable, I can add 10 to both sides. I don't need a calculator for this one. That gets me 11.4568 equals K. And that's my answer. Not very pleasant, this one. Not very pleasant at all, but that's how it's done. Okay, log base 7 of x plus 4 minus log base 7 of x equals 3. I see two log base 7s stacked up right next to each other, so why don't I combine them? If you have log base something minus log base something, you divide the inside, so this guy becomes log base 7 of x plus 4 over x equals 3. Now, I can't throw this into a calculator. I can't use the change of base formula because I can't find what the log base 10 of x's are. So what I need to do is rewrite this into exponential form. So my base is going to be my base here. Whatever it equals is going to be my exponent, and that's going to equal x plus 4 over x. 7 to the third power, that's a good one. 7 times 7 is 49. Let's not pretend that I'm plugging this into a calculator. 343, I knew that, is going to equal x plus 4 over x. Let's multiply both sides by x. So I now get 343x. So that happens, we get, you cross out x plus 4. So I guess the best thing to do is subtract x from both sides. Subtract x from both sides. That crosses out. That gets us 342x equals 4. Divide both sides by 342. Divide both sides by 342. That's gotta simplify to something. 342, 86? 1 over 86? Maybe? Well, my phone just dinged, so I'll take that as a sign. Let's keep it. 1 over 86, that's my answer. That was a nightmare, but a lot of fun. All right, time to solve. Negative 3 e to the stuff minus 7 equals negative 91. Fun little fact, I'm sure you already knew this, but log base e of x is the same thing as ln of x. Will that pop up here? I don't know, but yeah, probably it will. Let's add 7 to both sides. Let's scooch this over here. Negative 3 e to the stuff is now going to equal negative 84. Yeah. Now, not much I can do here. Oh, you know what I can do? I can divide both sides by negative 3. Let's do that. Let's divide both sides by negative 3. So now I have e to the 5a plus 1 equals positive 30. Nope. 28. 28. All right. That's a close one. Now, I can't do anything when I have variables living inside the absolute, or living inside an exponent. So what I can do is rewrite this as a log. Now, keeping in mind this happens, so what I could do is I could write out log base e, but I know log base e is the same as ln. So I have ln of 28 is going to equal 5a plus 1. ln of 28, according to the internet, which I'm using right now, currently is 3.3322. So this becomes 3.3322 equals 5a plus 1. Let's subtract 1. Let's subtract 1. And I now have 0.3322 equals 5a. Divide both sides by 5. Divide both sides by 5. And we're looking at something around a half. 2.3322 divided by 5, according to the internet, is 0.46644. That's what A is going to be. Delightful. Oh, stupendous. Wonderful. Grand. Gross. All right, my job is to solve ln of 5 minus ln of stuff equals ln of 33. Let's do this. Let's shove. Oh, no, I have a better idea. I have a wonderful idea. Let's connect these two ln's. Remember, ln is log base e, so ln follows all of the log rules. If I have a log minus a log, I subtract things in that order. So this guy becomes ln of 5 over 4 minus 4x. That's going to equal ln of 33. Now I have to be careful how I word this. What I can do is to make both of these ln's go away, I could take e to the of both sides. Why am I doing that? Well, e to the ln of stuff is just stuff. So e to the ln of 33 is just 33. I can multiply both sides by that 4 minus 4x, which is what I'm going to do. Multiply both sides by 4 minus 4x. This crosses out, leaving you with just a 5 on the left. Distribute here. 33 times 4 is going to be 132 minus 132x. Subtract 132, subtract 132, and 5 minus 132 is negative 127 equals negative 132x. Divide both sides by negative 132. Divide both sides by negative 132. Negative over a negative is a positive. And I'm pretty sure these guys don't simplify in any way, so I'm not even going to try. That's my guy. That's my answer. Fun, fun, fun. Jasmine invests $2,658 in a retirement account with a fixed annual interest rate of 9% compounded continuously. So this will require the continuously compounded interest formula, which is the total amount is going to equal your principal times E to the rate times time, also known as PERT, which is a type of shampoo. Now you know. So let's label things. You're my principal. You're what I start out with. 9% is my rate, but I'm going to write it out as a percent. So 9% is not a percent. As a decimal is 0.09. My T is going to be 15. And now it's just a matter of me putting it all together and throwing it into a calculator. So A is going to equal 2,658 times E to the 0.09 times 15th power. I'm going to move my mouse to the left and pretend that I'm not about to plug all this into a calculator and act as if I'm doing it in my head. And you get 10,253.037, so I'll do 04, which means $10,253.04. Now, if that seems like a lot of money, it's because it is. And it's because your rate is 9%. That is an unreasonably high number, but that's how you do it. And that's what we got. So we're done.